तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we learnt about ideal voltage amplifier, which we call as voltage controlled voltage source. Ideal current amplifier, then we said, is nothing but current controlled current source. Very simple terminology regarding what is meant by voltage control and what is meant by current control. We learnt, wherein if it is voltage control, obviously at the input port I is 0. So, that V I is what is controlling the voltage at the output, okay, as k times V I. This is what is appearing at the output, and the source has 0 resistance in series. It is a voltage source with 0 R naught output resistance, and it has a voltage which is k times V I. This is the characteristic of an ideal voltage amplifier. Then we said if it is current controlled, obviously R I is going to be 0 ideally, and therefore V I is 0 for the port, input port, which means it is basically controlled by II, and output current is going to be short circuit current, of course, is going to be k times II, and the source, current source, which is having k times II as the current, has a shunt resistance of infinity. So, this is where we had stopped, the current controlled current source, and we said in practice obviously we cannot have any of these ideal amplifiers. We have to know how we can recognize an amplifier as a current amplifier or as a voltage amplifier in practice. And then we said in practice we have a non-ideal source which can always be represented either as a voltage source in series with the resistance Rs, or as a current source Is, which is nothing but the short circuit current in the voltage source representation, and a shunt resistance of Rs. So, this representation, equivalent representation, does not mean anything. It is the same whether you represent it as a voltage source in series with the resistance or a current source in shunt with the resistance. Only thing is, ideal independent sources cannot have any equivalence. Ideal voltage source and ideal current sources cannot have equivalence. Non-ideal sources can always be put down as voltage source in series with the resistance or current source in shunt with the resistance. Now, if this is the current control current source or current amplifier, obviously in a practical current amplifier we will have some input resistance Ri, and what we want is that Ri should be a short circuit What does it mean? Ri should be such that it should take most of the Is, which is possible only when Ri is much less than Rs. And then we say that the input port is current controlled. So, you can contrast this with voltage control, wherein Ri was much greater than Rs. That was voltage controlled. So, once again current source output K times II, K times II is going to be shunted by a finite output impedance of the amplifier. This is the way you are representing a current source, non-ideal, at the output. This is a dependent non-ideal current source. So, it is going to be K times II shunted by R naught, and if it is a current source, then R naught is going to be much greater than RL. So, that most of this current still goes through RL and very little is lost through its output resistance. So, you can compare this with what we said can be considered as a voltage source, wherein Rs is much less than, that is R naught is much less than RL. So, this is the way we can distinguish between current sources and voltage sources practically, and current controlled and voltage controlled ports. Thereby declare these as either current controlled or voltage controlled at the input, or voltage source or current source at the output. Thereby distinguish for a given source combination and a load, the given amplifier can be identified as either a voltage amplifier or as a current amplifier. This particular aspect can be illustrated just as we did in the case of voltage controlled voltage source type of amplifier or voltage amplifier. Example 2, an amplifier with Ri equal to 1 kilo ohm is fed by an independent current source with source resistance Rs equal to 10 kilo ohm. Automatically now source resistance is 10 kilo ohm and input resistance of the amplifier is 1 kilo ohm. So, it can be declared as current control. If the short circuit current gain is 100, that means K is given as 100, and R naught of the dependent current source, this is the R naught, the dependent current source is 100 K, determine I naught over Is, that is the current gain, for a load resistance of 10 kilo ohm. Now, again since the load resistance is 10 kilo ohm and the current source resistance is 100 kilo ohm, it can be declared as a current source. So, this is definitely a current amplifier, and we can now solve this problem saying that the current Is now is going to be divided between this and this. Very little will go through this because we have chosen our parameters properly, so that it is acting as a current control source. So, II is going to be, this is 10 K and this is 1 K, this is 10 K and this is 1 K. So, 10 divided by 10 plus 1, which is 11, times Is. So, strictly speaking, if it is current control, we would have got this very close to 1. This would have been 1. So, that is the way to identify gain. Is, what part of Is is going into the amplifier truly as II? If it is close to 1, it is declared as current control. Again, this II is multiplied by 100 because of the current gain K is equal to 100, and R naught is 100 K, RL is 10 K. This 100 I is going to divide between 10 K and 100 K as 100 divided by 110. 100 divided by 110. As a result, we have therefore I naught equal to 10 by 11 square. This is one 10 by 11, this is another 10 by 11 into 100 times Is. So, we get the value of I naught over Is for this problem as about 100 reduced by factor 10 over 11, okay, because of the input problem, 10 over 11 because of the output problem. So, 10 over 11 squared into 100. Or if you want to express this as decibels, it will be 20 log this 10 over 11 whole squared into 100, which is of course pretty close. This being close to 1, this is about 2 into 20, which is 40 decibels. So, this gain now can be more exactly given as 20 log to the base 10 100 minus, because actually plus 20 log to the base 10 over 11 whole square. This is less than 1. So, this becomes minus, and therefore, 11 over 10 square. So, this is equal to the same 40 minus, this is evaluated, comes out to be 1.66. So many decibels, which we had approximated earlier as 40 decibels. Now, coming to the power gain, which is defined as P naught over P I, which is nothing but V naught I naught divided by V I I. This can be either represented solely in terms of voltage gain or current gain in the following form. V naught is nothing but R L into I naught, actually magnitude if you take, because there is a negative sign. R L into I naught is V naught, I naught squared, and then V I is I into R I. So, R I into I I squared. V naught is R L into I naught, V I is R I into I I. Replacing it with this, we know that the power gain is same as current gain squared into R L by R I, which is nothing but R L in our case is 10 K and R I is 1 K. So, that times the current gain, which is already known to be 100 into 10 100, okay, into 10 by 11. This current gain is the current gain from input to output, not I naught over I s. Okay. That is what we had evaluated here. So, I naught over I I is nothing but the actual short circuit current gain is 100, then it gets divided between R naught and R L. So, that factor of 10 by 11, this squared. So, power gain in decibels is 10 log base 10 of this factor, which is 10 into 100 squared to 10 by 11 squared, which is going to be equal to 10 log to the base 10, 10 to power 5 minus 10 log to the base 10, 11 by 10 squared. The same factor log to the base 10, 11 by 10 squared has been earlier evaluated, and therefore, you can use that information. This is very close to 50 decibels. So, please find out how close it is to 50 decibels. Okay. We have the same factor evaluated earlier. Okay. So, this is the power gain. So, you know about current gain, voltage gain and power gain, the three important parameters associated with any amplifier. For any amplifier, we should be able to evaluate this in terms of decibels normally, so that we know the performance of our amplifier, whether we need one amplifier to fulfill our requirement or two amplifiers. That can be readily found out from how many decibels is your requirement in terms of amplification. If it is 100 decibels in terms of amplification that is required for power, then you know that two such stages must be cascaded. If it is 150, three such stages must be cascaded. We will discuss this later, how to do cascading to improve the power gain of stages. Okay. Now, we have yet to finish our discussion on amplifiers, the types of amplifiers. We have just discussed voltage amplifiers and current amplifiers. We have to now discuss about two other important amplifiers, ideal amplifiers. So, we discussed voltage amplifier, which was an ideal voltage controlled voltage source. We discussed ideal current amplifier, which was ideal current controlled current source. Just as ideal voltage source cannot be represented in terms of ideal current source, these voltage source and voltage amplifiers and current amplifiers are unique by themselves. They cannot be represented by the other method. But a non-ideal amplifier, on the other hand, can always be represented as a voltage controlled voltage source or current controlled current source. That kind of equivalent circuit can be put. But what it is really is determined by basically how it is driven by means of the source and how the load is connected. So, now the other two, obviously you must have thought of readily, possible amplifiers are when the input port is controlled by voltage, but output port is having not voltage source but current source. This is ideal voltage controlled current source, wherein Ri is infinity or Ii is 0. Then this being a current source, R0 is also infinity, and it is going to be controlled by current output, which is I of that, is going to be transconductance G. This is conductance, and it is a transfer from input to output. That is why this is called transconductance. So, this G times V I. R naught is 0. So, this is basically called a transconductor. As against voltage amplifier, where the forward transfer parameter from input to output was voltage gain here. In this case, it was current gain. In this case, it is transconductance. And this amplifier is called transconductor amplifier, which is gaining popularity in present day integrated circuit designs. Okay. As against this, we have ideal. Instead of voltage control, it could be current controlled at the input port, and at the output port it could be a voltage source. It is a current controlled voltage source amplifier. Let us see. Current control means Ri of the amplifier is 0, and it is current control. Therefore, we have just as I 0 here, V I equal to 0, and it is a voltage source. So, voltage is equal to R resistance times I, the input current. So, this is therefore called, just like this, transconductance. This is trans resistance. Just see, trans resistance, or this whole thing is called trans resistor amplifier as against transconductor. So, trans resistor, you have an abbreviation transistor. That is how transistor derives its name, but it is really not ideal current controlled voltage source. It is close to ideal current controlled current source. We will discuss it later. But transistor derives its name from transfer resistor. So, it is one of the ideal amplifiers here. We have here voltage source. So, R naught is equal to 0. So, this characterizes the two important amplifiers which have been left out: current controlled voltage source and voltage controlled current source. So, now let us consider the two different amplifiers which we have discussed. One is transconductor amplifier and trans resistor amplifier. When again the amplifier is not ideal, just as we considered earlier voltage amplifier and current amplifier. How do we recognize that a particular amplifier belongs to a particular category? That is going to be done here also. It is voltage controlled at the input, which means Ri earlier was infinity in the case of ideal amplifier. Here Ri is much greater than R, yes, that is voltage control. It is current source at the output, that means R naught is much greater than RL. So, under this situation, under this drive, source impedance being fixed like this and load impedance being fixed like this, or when input impedance is suitably chosen such that it is this way and output impedance of this is like satisfying this condition, then we call it a transconductor amplifier. And the most important parameter of interest at that point of time is the transconductance. However, we can still evaluate the voltage gain and current gain for this circuit, okay, just as we did on power gain again for this circuit in the same manner as we did earlier. Okay. Even though the important parameter associated with this has to be recognized as transconductance. We can just see that a transconductor amplifier is pretty close to a practical field effect transistor amplifier, where field effect transistors are traditionally voltage controlled devices, and the transconductance GM, small gm it is known as, is what is important as parameter for a field effect transistor, and the output resistance R naught is typically of the order of tens of kilo ohms, and therefore, for resistances of the order of hundreds of kilo ohms, okay, it can be acting as a voltage source, but resistances of the order of kilo ohms, it can still act as a current source. So, basically a field effect transistor belongs to this category, and as I told you, a bipolar junction transistor, strictly speaking, the common base amplifier which we will see is current control current source. A common emitter can be pretty close to this amplifier, where Ri is not really infinity, Ri is maybe of the order of tens of kilo ohms, okay, and therefore, for source resistance of the order of kilo ohms, it can be still considered as voltage controlled, and it is strictly speaking a good current source, where R naught is of the order of hundreds of kilo ohms for BJTs, bipolar junction transistors. So, for load resistances which are typically of the order of tens of kilo ohms, the BJT can be still considered as a current source output. So, here it can become voltage controlled if it is a common emitter amplifier. If it is a common base, on the other hand, it is strictly current controlled at the input and current source at the output, and therefore, it is a current controlled current source. So, we have later ample opportunity to identify the various devices that we are going to use as amplifiers as one of these, depending upon the type of source resistance and type of load resistance. This is something that you have to understand very well at this juncture itself, so that you are not confused as to what exactly is belonging to what category out of these four. So, again here this is a current controlled voltage source, this is a voltage controlled current source. So, current control means Ri is much less than Rs and R naught is much less than RL. Develop that. Trans resistance, the transfer resistance is what is important here. Still, just as in the other cases, we can evaluate the voltage gain and current gain and subsequently the power gain of this stage. And as I told you, the this kind of transfer resistor amplifiers are not all that common practically. Most of the amplifiers which have been designed in present day, either they are going to be voltage controlled voltage sources or this transconductor types. Very few of current control current source type as well as this current control voltage source type are in existence, but with the advent of new designs in integrated circuits, the current control current source has become very popular, and recently people have attempted to design current control voltage sources as well. So, traditionally we have been taught only about voltage controlled voltage source as amplifier. However, we have now recognized the existence of four types of amplifiers, ideal amplifiers, and these four types of ideal amplifiers cannot be exchanged in terms of I will represent it in this manner or I will represent it in this manner. These are unique by themselves. When a non-ideal amplifier exists, then we can represent that non-ideal amplifier by any one of the 4 categories. Now, what it is going to be out of the 4 is going to be really decided when RS is fixed and RL is fixed. So, let us now summarize what we have been discussing so far. There are 4 types of amplifiers: voltage controlled voltage source, which is called voltage amplifier; current controlled current source, which is called current amplifier; these are what are called duals. One is the dual of other. Okay. We have then voltage controlled current source, okay, which is called transconductor amplifier. And current controlled voltage source, which is transresistor amplifier. These are once again what are called duals. What is a dual? Let us recollect what we have learnt in our networks. R, dual of R is G. Dual of a resistor is a conductor. Dual of L is C. Dual of C is L. Okay. Dual of a voltage source is current. Dual of current source is voltage. These are what are called duals, right? So, now I told you about cascading. Cascading means what? Connecting one amplifier to another amplifier so as to get obviously increased power amplification. This is what it is. You are not happy with whatever the one amplifier is giving. You would like to connect one amplifier in cascade with another amplifier. So, let us see how cascading is done. This is amplifier 1 is cascaded to amplifier 2, and then we are connecting, let us say, the load, and this is the first amplifier which is driven by the source, non-ideal source, whether it is voltage source or current source, both are, let us say, non-ideal, then it does not matter which one we use for representing it. So, amplifier 1 is said to be cascaded to amplifier 2, forming an overall amplifier, okay, which will give you better performance in terms of forward transfer. Right. As the transfer is concerned, we said each of them is unilateral. What it means is transmission is there only from input to output, from this input to this output. Therefore, overall transmission is from this input to this output. Okay. There is no connection from here to here, that is back. Okay. The reverse transmission is not there. So, these are all unilateral circuits. In such a situation, it is very easy to show that the amplification factor is improved. So, now let us try to evaluate, for example, the voltage amplification factor here, okay, and current amplification factor here as well as here, because these are two different types where the voltage amplification and current amplification have not directly made an appearance. Right. So, after that we will cascade the non-ideal amplifiers together. So, these non-ideal amplifiers again could be represented in any one of the 4, and they will be called a particular type depending upon what kind of source and load we have. Now, you can see that as far as load for this is concerned, it is going to be the input resistance of the amplifier 2 which will act as the load for amplifier 1. So, it is the input resistance of this Ri2 which will act as the load for amplifier 1. And also as far as the amplifier 2 is concerned, look at it at this point, this is the point, okay, where it is looking at a source. As far as this is concerned, this is the feed for the amplifier 2. So, this amplifier 2 can only look at this amplifier 1 as a source. It does not know whether it is an amplifier or a source, it cannot make a distinction. So, we can represent this amplifier 1 with the drive there as a source, okay, for this. That means, output resistance of this is going to be the source resistance for this. So, this can be represented as a voltage source in series with some output impedance which will be really the source resistance for this. So, you have to make a distinction now when we connect an amplifier 1 to amplifier 2. For amplifier 1, amplifier 2 is the load. For amplifier 1, amplifier 2, for amplifier 1, amplifier 2 is the load. Now, that means load is not really necessarily a resistor, right? It can be an amplifier. So, for amplifier 2, amplifier 1 is the source. That means, I should be capable of representing amplifier 1 output as a source, voltage source in series with the resistance, or current source in shunt with the resistance, that is all. Now, you can see here, take any amplifier, this output of the amplifier is already represented as a current source in shunt with this resistance R naught. So, this load can be removed now. This will be going to another amplifier where RL is going to be the input resistance of the next stage. It is already represented as G times Vi shunted by R naught. Or if you think that this should be represented as a voltage source, you can represent this. So, I will make the alteration here. G times Vi shunted by R naught can be represented as a voltage source in series with the same resistance R naught, okay. But this voltage is now going to be G times Vi into R naught. It is nothing but what is defined as open circuit voltage of the source, that is G times Vi times R naught. Okay. So, now you see I have represented this as a voltage source with G times Vi times R naught, okay, and you will call this G times R naught as the open circuit voltage gain. So, now this was voltage controlled, this has now become a voltage source, and this is now G times R naught is what we have earlier defined as K. So, this is K times Vi. So, now we have already evaluated for such a voltage controlled voltage source the voltage gain and current gain. Okay. So, the same expression is valid for voltage gain and current gain, except that K has to be replaced by G times R naught. Is this clear? Next, let us see that this is already a voltage source. Now, the voltage here is R times V I. I would like to represent this in terms of V I. Let us say this is really the V I of this stage. So, I know that V I is nothing but I into R I. Right. So, I is nothing but V I by R I. So, now, this has been already represented as a voltage source. Okay. Now, if it is voltage controlled, the voltage here should be this voltage V I times some K. So, it is K times V I. So, K is now represented as R divided by R I. That is the only difference. And now, all those expressions for voltage gain and current gain that we have derived, okay, when we discussed current amplifiers and voltage amplifiers are valid here, and the power gain also is valid, as long as the factor K is replaced by R divided by Ri. So, as far as analysis is concerned for the non-ideal amplifier, it is enough if you do the analysis of one type of amplifier. All those things that are discussed for that can be still made valid depending upon how you look at the equivalent circuit. So, K in this case has been G times R naught, where G is the transconductance value and R naught is the output resistance of the amplifier, and K here is nothing but R, which is the trans resistance, divided by input resistance Ri. So, with this, what all we have discussed in our analysis in earlier situation becomes valid. So, I would like you to work out a problem. The problem is problem 1. Determine V naught over Vs, okay, or let us say I naught over Is for Vc Cs and Cc Vs. Okay. When these are non-ideal. So, please work out this expression. Okay. The hint that is given here is that the expression that you have derived earlier for V naught over Vs in the case of voltage controlled voltage source, I naught over Is in the case of current controlled current source become valid, except that you have to replace in the case of voltage controlled current source the K by G R naught, and in the case of this current controlled voltage source the K by R over R. Okay. Except that. So, if you work out this, you will understand that all these amplifiers can be used interchangeably as long as they are non-ideal. And also you will understand and appreciate what the load means. Load is always the input impedance of the amplifier, okay, when it is an interface like this between amplifiers, two amplifiers, and the source is the output resistance, okay, in series with voltage source, okay, if it is a voltage controlled representation, R naught shunted by a current source if it is a current controlled representation. they can be used interchangeably. So, this is the information about cascading. Another important, we would say, theorem that we can derive while cascading is, what is I naught over II? Let us say we call it as current gain, AI. AV is V naught over Vi for the amplifier. Okay. This is for the amplifier, amplifier current gain, amplifier voltage gain. Then this is called with transducer, right? That means I naught over Is, okay, and V naught over Vs. We will call this as AIS, okay, and AVS distinction. This is the short circuit current for the transducer. This is the open circuit voltage for the transducer. Here we are ignoring the effect of the source impedances. Okay. In this case, okay, the source impedance is, let us say, so high that most of the current, okay, goes into the amplifier. In this case, source impedance is so low, most of the voltage comes across the input. So, this is a basic difference between I naught over II and I naught over Is, V naught over Vi and V naught over Vs. Always V naught over Vs is going to be greater than V naught over Vi by a factor which is going to be determined by Ri by Ri plus Rs. Okay. Same thing is case. AIS is going to be greater than AI, okay, that is AIS into Rs divided by Rs plus Ri is what is going to be the factor. Involved in both, there is no difference in the factor. Factor is the same. Okay. Now, I want to prove an important theorem in cascading. What is it? V naught over Vi, okay, I would like to represent it in terms of current gain. So, V naught is nothing but I naught, okay, into RL, always, okay, the magnitude. Let us consider magnitude. It is negative actually. Then Vi is nothing but II into Ri. This we have used earlier in the example also to obtain the power gain, okay, in terms of current gain. So, voltage gain of any amplifier AV is equal to AI, current gain of the amplifier, into RL by Ri. Okay. This is an important statement. So, suppose I am cascading. So, if I am cascading, at the cascading point, RL is another amplifier is equal to Ri. Please remember, the load for one amplifier, okay, is same as input resistance of the other amplifier. So, RL is equal to Ri. Then it is proven that AV is always equal to AI. This is an important statement. While cascading, therefore, okay, the voltage gain is same as current gain. That means, if an amplifier is capable of giving voltage gain but not current gain, or vice versa, if it is giving current gain but not voltage gain, then it cannot give either voltage gain or current gain when it is cascaded. An amplifier that is cascaded, if they are identical amplifiers, right? If they are identical amplifiers, okay, it should be capable of giving both voltage gain and current gain in order to give any one gain, okay, because current gain is same as voltage gain if identical amplifiers are cascaded. Because input resistance of one amplifier, okay, becomes the load of the other amplifier. Okay. So, if they are identical, its own input impedance is same as load. Okay. So, this something common sense thing that you have to remember, that when I cascade, if I cascade identical stages, the stage that I use must have both voltage gain and current gain, then only it can act as power amplifier. Right. This is an important statement, profound in its, okay, sort of effect in design. Therefore, I must not cascade amplifiers which give either voltage gain or current gain if I am using identical stages. I must use amplifiers which give both voltage gain and current gain, okay, so that when I cascade, current gain becomes equal to the voltage gain and it is greater than 1, and therefore, subsequently it will give you power